All right, everybody, we're going to get started now. The theme of Panel 1A is Water, Cities, and Infrastructure, and we're so fortunate today to have three experts in these areas with Peter Gleick, David Sedlak, and Dave Sunding. We've asked each speaker to go for about 20 minutes, and then afterwards we'll have Q&A. My name is Dick Luthy. I'm a professor at Stanford University. I work in the area of water quality engineering. And with Dave Sedlak, we are the director and co-directors of a large National Science Foundation center on the theme of reinventing the nation's urban water infrastructure. Just one word about me. I think if you were to scratch below the surface of many Stanford professors, you would find that they bleed blue. In my case, I have 3 degrees from Berkeley. I'm a product of the 60s at Berkeley. And in chemical engineering and College of Chemistry, we call ourselves from that era the free radicals. All right. Our first speaker this morning is Peter Gleick. Peter is affiliated with the Pacific Institute for Studies in the Development, Environment, and Security. He was the co-founder of the Pacific Institute, which just recently celebrated its 25th year anniversary. The Pacific Institute is an independent, non-governmental organization specializing in field of water, economic, environmental justice, and sustainability. Peter is an expert in the area of water policy and management. He's been recognized by a MacArthur Prize. He's also been, which is very prestigious, he's also been recognized by election to the National Academy of Sciences. Most recently, in 2012, he published the book, A 21st Century U.S. Water Policy. And with that, Peter, welcome.
Good morning, everyone. I guess you sort of have to start with your Berkeley credentials or something here. I'm an ergie, woohoo, ergies. If you don't know what an ergie is, you should. I'm not going to describe it. I've known Dick for many years. Dick and I were on the Water Science and Technology Board at the National Academy, and I'm on the Science Advisory Board of the Renewable project at Stanford and Berkeley as well. I'm going to talk about this: why focus on supply is not a solution to our water problems. So that's my conclusion. I mean, I'm not saying you can go to the next session now, but that's my conclusion. It doesn't say supply isn't an answer. It says why a focus on traditional supply options isn't going to solve our water problems. And I have a lot to say. I'm going to go through it pretty quickly to just give you a sense of what I mean. I'm going to talk about what I mean by supply. I'm going to talk about the concept of peak water, which is a concept we've been working on at the Pacific Institute here in Oakland. And then I'm going to talk about some alternatives to that viewpoint of a supply-focused answer to our water. And I'm going to focus on California, but I would argue that much of what I have to say, not everything, but much of what I have to say is relevant for much of the rest of the world as well. So, supply. In the 20th century, water supply meant more water. Build another aqueduct to move water from where we have it to where we want it. Drill another groundwater well to tap an aquifer. Build another dam to store water that we get in wet seasons so we can use it in dry seasons. Supply, that's what we, and I have an engineering degree. I was trained in hydrology and climatology. That was the way we were taught to think about water, and that's brought enormous benefits to us, that focus on supply. California wouldn't look like California today if we hadn't invested in these kinds of infrastructures that move water from the north to the south and store water in the wet season for use in the dry season and so on. And I'll come back to some of that. But that's what traditional supply meant. Let me talk about the concept of peak water before I come back to this idea of supply. And let me do it in the context of curves that all of us are familiar with. Exponential curves that you all know are frankly behind many of the problems that we face today. Global population, described by an exponential curve. This is the population curve for the last 1,000 years, from 1000 to 2000 AD, showing exponential growth in population. Carbon dioxide in the atmosphere over the last 1,000 years. And we heard some talk quite a bit about climate in the first session this morning. Atmospheric concentration of CO2 in the atmosphere over the last 1,000 years. Exponential growth behind many of the problems that we face today. Exponential growth followed by a peak in something, followed by a decline. Again, we saw lots of curves this morning, and you see in lots of the sciences that you deal with this kind of graph as well. We see it with US oil production, and the concept of peak oil is this curve. And this is a graph actually of peak oil production in the United States. Oil production in the US peaked in the 1970s, actually in 1970, I think, and has declined since then. And there's a debate about when the world is going to reach peak oil. Peak oil doesn't mean we're going to run out of oil. It's going to mean it's going to become more difficult to find or more expensive to produce, and alternatives will become cheaper and production will decline. But an exponential growth in something, a peak and then a decline, follows this classic shape. Atlantic cod. Again, this is, you can't read the numbers, but 1950 to 2010, cod production, exponential growth in the taking of cod in the Atlantic, followed by, in this case, a collapse in the cod population and a decline in cod capture. And even to this day, the cod population in the Atlantic hasn't recovered. So demands on resources, peaking in resources, and a collapse or a decline in something follows this kind of curve. And the third curve is the classic logistics curve, exponential growth in something, a leveling off, and then a sustained something. We see this in technology all the time, market penetration. This is market penetration over the last 100 years of landline telephones. Somebody invents something, telephones, cell phones, DVDs, all sorts of technology follows this curve. People love them, they buy them, and then everybody's got one. And you're not going to buy, maybe you'll buy two of them, but there's a leveling off of the market penetration, typically around 100%. Or ecosystem carrying capacities follow this kind of curve. Or back to water, this is cumulative dam capacity, storage of volume of water stored behind dams in the United States. I'll show you a bigger picture of this a little bit later for California. But we learned how to build big dams from a technical point of view. The money was spent to expand storage capacity behind reservoirs in the United States in the 40s and 50s and 60s and 70s when the big dams in the United States were built, and then a leveling off for a variety of reasons. And I'll come back to those in a moment. Another comment about peak water, and this is all in the context of some work I've done with a colleague of mine, Meena Palaniappan, on the concept of peak water. Water is a renewable resource, mostly. A renewable resource is typically defined as a resource that is flow limited. A non-renewable resource like oil is typically defined as a resource that's stock limited. The difference being that non-renewable resources, or the amount you can use, is limited by the amount that's there, the stock. Once it's gone, it's gone. It's non-renewable. Renewable resources are limited by flow. The amount that you use has no effect on the amount you get next year. Think about a river. Natural flows, the hydrologic cycle. Doesn't matter if you take water out of the river this year. It doesn't affect how much water you get next year. There's natural variability and so on. But you can't take more than is provided. You can't take more than the natural flow. So renewable resources are flow limited. Water, interestingly, is mostly renewable, but it has some non-renewable characteristics. And in this concept of peak water, that's relevant. And I'll talk about that in a second. So peak renewable water sort of looks like this. You start to take water out of a river. Your demand grows because your demand for industrial water use or agricultural water use grows. And then you take it all. And you can't have any more. Once you take the entire renewable flow of a river, you're constrained. And that's peak renewable water. And we see this on the Colorado River. We see this on lots of rivers. And it begs the question, of course, should we take it all? That's an ecosystem question, it's a societal question, it's a cultural question. There are lots of issues associated with that. But that's the concept of peak renewable water. And in more and more of our resources, our traditional response to demand for supply, find more water, is running into constraints. This is the flow of the Colorado River measured at what's called the southern boundary station, which is basically at the mouth of the delta in Mexico. And what it shows is, first of all, lots of natural variability. We have wet years and we have dry years. What it also shows is that in the 30s and 40s and 50s and 60s, the amount of water reaching the delta started to decline. And that's because we built the big reservoirs on the Colorado River and we started to take a lot of water out for our cities and our agricultural demands on the Colorado. And what it also shows now is that in average years, or in typical years, no water reaches the Colorado River Delta anymore. We take it all. We, the 7 states and Mexico. In really wet years, sometimes if the reservoirs are full and then you get a wet year, some flow reaches the Delta. But mostly, we've reached peak demand and peak supply on the Colorado River. And this is true on the Yellow River and the Nile and the lots of ecosystems around the world. Peak non-renewable water looks like this. You take water out of an aquifer, you take more and more, and then the groundwater levels drop, it becomes more expensive to pump, and you run into a peak and you start to reduce withdrawals because it's more expensive. Land goes out of production, like in the Ogallala aquifer, and you start to get a decline. And that's peak non-renewable water. And a lot of our water worldwide now, a lot of our use worldwide is not peak renewable water, but it's peak non-renewable water. And that's another topic for another conversation. And then there's the concept of peak ecological water, which I won't discuss much, except simply to say that it's the idea that we reach a point where the next gallon of water or cubic meter of water that you withdraw from a system causes more ecological and economic harm than provides benefit. So benefits, growing benefits with the more water you use, amount of water appropriated by humans, until all of a sudden the next unit of water you take has negative economic or ecological, or preferably a combination of ecological and economic value. We're good at measuring economic value, we're crappy at measuring ecological value, but that's a question for ecological economics. And that's the concept of peak ecological water, and we argue lots of systems around the world are way past the point of peak ecological water, where we're now causing more harm than we get benefit out of the water we're taking out of those systems. So quick overview on that. I'm not going to be able to take questions till later, unless I've said something totally stupid.
I was just going to say, so what does it look like during the time of decline like that?
Okay, well, we can talk about that later. So, peak water doesn't mean we're going to run out of water. Water is a renewable system, mostly. Where it's non-renewable, we are going to run into stock constraints, and there are limits on what we're going to be able to do in the future. And we are running up against flow limits in renewable systems that are a combination of natural flow constraints and increasingly economic, and I would also argue ecological constraints. And we're hitting peak ecological water in lots of our systems. So what does this mean for traditional supply? California. This is a spaghetti diagram. Lots of you have maybe seen it before. The different colors are the different kinds of infrastructure we have. One of the colors is our federal system. One of the colors is our state-built system. One of the colors are local systems. I'm not even going to look to see which are which. But we've built a lot of traditional supply that's permitted enormous cities in coastal areas far from our sources of water. And that traditional infrastructure has brought enormous benefits to us and some unexpected costs. Part of the problem is this picture. This is withdrawals from the delta, the amount of water we withdraw from the delta from 1956 through last year. And it's the Central Valley Project in blue and the state water withdrawals in red and other delta within delta withdrawals in green. There's a lot going on in this picture, and if how you think about this picture depends on your perception. So, some people look at this graph and they go, oh my God, look at this. There are periods of times when our withdrawals from the delta plummet, and not everybody gets to use as much water as we would like. And some agricultural users are low water rights users and they lose water during droughts. These are droughts, basically. The most recent drought, the 87-92 drought, the 76-77 drought. When there's not enough water, not everybody gets all the water they want. Oh, that's a real problem. Somebody else looks at this graph and goes, well, it sort of looks like we're taking more and more water out of the delta all the time on average. And maybe that's a problem. Maybe we're taking too much water out of the delta. Some people look at this and anyway, there are lots of ways of looking at this, but this is part of the Rashomon picture of our water situation. I'm arguing that the traditional approaches, the dams, the aqueducts, the groundwater withdrawals, are not going to solve our water problems in the future, that we have to think about something different. This is a picture of dam. These are GIS map all the dams in California. There are thousands of them. Okay, maybe we could squeeze in a few more on some of the rivers in between existing dams, which are some of the proposals, or off-stream dams, or raise existing dams. There are lots of proposals out there. But I'm gonna, it's an opinion, I'm gonna state that I don't think that would solve our water problems. This is a blow-up of that logistics curve I showed you for the nation, for reservoir storage. This is California. Total cumulative capacity, water stored behind California dams over time. And you can see we started to build big dams in the 20s, 30s, 40s, 50s. Here we built Shasta, big increment to storage behind dams. And Trinity Dam and Exchequer and Oroville, the keystone of the state water project. This is the federal water project, and so on. And then it sort of leveled off. Because, why? Well, we built on all the good dam sites, and some not so good dam sites, one might argue. Federal money and state money for new projects dried up. We started to realize the ecological damage, the peak ecological issues associated with building big on-stream storage. And there was growing environmental movements, David Brower among them, who raised awareness about the ecological costs, not the economic benefits, but the ecological costs of this infrastructure. Lots of reasons. But the bottom line is that, okay, and up here I've plotted the most likely new additions to storage that have been proposed. Raising Shasta a couple of feet or more, building Sites Reservoir, which is an off-stream storage in the North Delta, squeezing one more dam on the San Joaquin in between two existing dams. Those are the three new big storage options that have been proposed. I don't know if any of them will be built. If all of them are built, we get this additional increment. And I don't think there's going to be much beyond that. We're not going to make this curve exponential again. Even if we wanted to, that's not going to happen. That's one of the reasons why I think new traditional supply is not necessarily the answer. We're overpumping groundwater. This is a map, a little hard to read, but basically shows those areas where non-renewable groundwater withdrawals are occurring, especially the lower San Joaquin, where we overpump statewide, on average, 1 million or 1.5 million acre feet of water a year. That's not sustainable. Groundwater levels are dropping, streams are drying up, ecosystems are suffering. We can do that for a little while longer, but it's unsustainable. It's got to stop. And where are we going to find another 1.5 million acre feet just to replace that overdraft? Much less are we going to expand supply with more groundwater pumping? I would argue no. Climate change, I'm not going to talk about this much. You heard a lot about it earlier, but climate change is going to screw up our existing hydrologic cycle in ways that you heard about this morning. We've done a lot of work on that at the Pacific Institute. We're not adequately planning for those changes in the hydrologic cycle that we're now confident will occur, especially changes in the timing of snowfall and snowmelt runoff on our rivers. So if traditional supply isn't going to work, what do we do? And this is solutions. I think there are other things that we can do. First of all, I'm not saying new supply isn't a good idea. I'm saying traditional supply isn't going to solve our problem. But there are lots of new ways of thinking about supply. Conjunctive use. Recharge some of those groundwater aquifers, treat them like reservoirs, fill them up in wet years. You don't lose water to evaporation, and pump them more in dry years. That's conjunctive use, and there are interesting experiments going on already in California in that area. Treated wastewater. There's a million acre feet probably of treated wastewater, treated to different standards that we collect, treat, and throw away. That's a new source of supply. It's an asset, not a liability. Innovative water transfers among different users, desalination when we can deal adequately with the environmental and economic challenges of desalination is a potential source of new supply for certain areas. Rainwater harvesting, there are lots of new things we can do that don't require building new dams and aqueducts and overpumping groundwater and so on. So supply, but not traditional supply. I think more important is demand. Let's do more. The short version here is let's do more with the water we're already using. That's a question of productivity, conservation, efficiency, and so on. Dick, how am I doing on time?
Doing all right. We should wrap up pretty quick, though, to leave time for the other two speakers and
Okay.
questions.
We have to rethink management. Our traditional 20th century systems are not going to work for a 21st century California. And there are lots of options there, which perhaps we can talk about later. But a couple of quick comments about, I've talked about new sources of supply. I want to leave you with the demand, some thoughts about demand. This is related to supply, but when you have a leaky bucket and the stuff you're putting in at the top is scarce and expensive, increasingly expensive, I would argue the first thing you do is you plug the leaks. And that's the argument for efficiency and conservation. And it's not brown lawns and shorter showers. We do those things in an emergency. Mayor Villaraigosa talked about the restrictions on outdoor landscape watering. Okay, we do those things in an emergency. But what we're talking about is not lawns, but efficient landscapes, native landscapes. We're talking about efficient appliances and toilets and shower heads and washing machines that do the things we want to do with less water. That's productivity, not deprivation. In 1980, 100% of the toilets in California were 6-gallon per flush toilets, because that's the technology that we had. And then California passed, before the national government passed, efficiency standards, and we started implementing 3.5-gallon per flush toilets, and then 1.6-gallon per flush toilets, ULFTs. And by the year 2003, the Pacific Institute estimated, all right, this is the distribution of toilets. We still had a bunch of old, inefficient toilets, and these were no longer the most efficient toilets, but increasingly we were putting in place ULFTs. New construction, you had to put in an efficient toilet, and so on. By 2020, it might look like this. Most of our toilets will be 1.6-gallon per flush toilets. We'll still have a reservoir, if you will, of inefficient, really inefficient toilets. And now there are new, maybe the colors shouldn't have been the same here, but new high-efficiency toilets that aren't 1.6 gallons per flush, but 1.2 gallons per flush. So technology changes, penetration rates change, and so on. There's enormous potential for tapping into wasteful uses of water. All right, so let me give you some final thoughts. Our assumptions that the past is a good guide to the future are no longer valid. The 21st century is not going to look like the 20th century. Climate change, population dynamics, the economic systems we have in place, and sources of financing, the past isn't a perfect guide to the future. Traditional supply options are extraordinarily limited now, here and increasingly around the world, and are not going to solve our problems. There are strategies, though, for reducing our vulnerability to peak water limits and to climate change, and they include innovative sources of supply and a focus on demand and new management techniques and strategies. But we're going to have to think differently. And we're not thinking differently. Water policy in the state of California, even today, is mired in the old thinking. The new California water plan that was just released this week takes steps in the right direction, but in my opinion, they're too slow. And we're going to have to do things differently and more quickly if we're going to prevent the problems that I think we see are coming. Thank you very much.